All right, everyone. Welcome to the May TEPS seminar. We're just going to get started. So I'm going to pass it off to Haley Sapers first to introduce our first speaker, Grace. Haley, go ahead. Oh, Haley, you're muted.
Sorry about that. Hello, everyone. I've had the honor and pleasure of working with very talented master's student, Grace Bischof, over the past 2 years. Grace is a master's student at York University, working in the Planetary Volatiles Lab under the supervision of Professor John Moores. Grace's work involved water ice clouds as seen during the Phoenix mission on Mars. Specifically, she is constructing a record of water ice clouds throughout the mission by modeling the air temperature obtained with a MET instrument. Grace is also a part of the Mars Science Laboratory, or MSL, mission science team, completing science operations for the environmental science theme group. So I have the pleasure of introducing Grace.
Thanks, Haley. So I will share my screen and get started. Okay, everyone can hear me okay? Okay, sounds good. So as Haley mentioned, the talk that I'm going to give today is about creating a record of water ice clouds throughout the Phoenix mission, and that is derived from modeling the MET temperature data. So just a brief introduction to Mars' atmosphere. I know a lot of people here are more so exoplanet people. So the Martian atmosphere is very thin, and it's primarily composed of carbon dioxide and has trace gases such as water vapor and methane. The atmospheric phenomena happening on Mars are variable over a Martian year. So similarly to Earth, the planet has an axial tilt. And so this causes differences between the northern and southern hemispheres. And differently than Earth, Mars has a bigger eccentricity, and so it's closer to the sun at perihelion, where the global temperatures tend to be a bit warmer, and you have enhanced dust lifting, and it's further from the sun at aphelion, and the global temperatures are a little bit colder, and you get increased water ice cloud formation. We can study these cloud, gas, and dust activities and interactions on Mars to give insight into the weather and climate of the planet. So this project specifically is focusing on the cloud activity and interactions. So we've been monitoring clouds on Mars for quite some time. You can see them from Earth's orbit using Hubble, for example, from Mars's orbit using some of the different orbiters, and from Mars's surface. So this is an image taken with the Curiosity rover. And we have determined quite a bit about water ice clouds, but there definitely still is a question when it comes to how these clouds interact with the climate and what effect these clouds have on the weather, the temperature, and all of that. So this project will be looking into that, and it specifically uses data from the Phoenix mission. So the Phoenix mission landed in the northern Arctic of Mars in 2008. As you can see from this photo up here, it's the most northern lander that's ever been put on Mars, and it had the explicit goal of studying the water cycle in the polar region. Phoenix operated for 151 sols, and it operated through summer solstice and into the midsummer. Phoenix monitored the local weather conditions. It had a LiDAR on board, it had temperature and pressure sensors, and it had a camera called the Surface Stereo Imager. And with Phoenix, we were actually able to see clouds many times. So this image on the left is images of clouds captured by the SSI in Sol 119, and you can see them nicely drifting across the screen there. And the LiDAR was a really essential tool actually for finding out cloud information throughout the mission. So this is LiDAR data from Dickinson et al. 2010, where they were able to piece together a cycle of water ice clouds. And so they noted that water ice clouds tended to form in the evening and strengthen throughout the night, and then dissipate into the morning as the temperatures warmed up. And with that, they were able to find the water ice optical depth and the height of clouds. Fault streaks or snow-like precipitation was observed for the first time with the LiDAR. And so it was a really crucial instrument for understanding water ice clouds. However, if we zoom in on this picture a little bit more, you can see that there are some gaps in this data, and it begs the question of, were there no clouds forming at this time, or was the LiDAR just not used? So spoiler alert, the LiDAR just wasn't used sometimes due to power constraints towards the end of the mission, as the sun was not beating down so heavily on the solar panels. The LiDAR was precluded from nighttime operations. And in addition, the LiDAR wasn't used overnight until Sol 38 of the mission. And so any clouds that were to form overnight in those first 38 sols, that would be missed entirely in the data. And so this work seeks to fill in these temporal gaps. So one thing to know about clouds and how they interact with radiation is that they can participate in radiative forcing. So here is just a very simplified energy balance where the two strongest components of the energy balance on Mars are the incoming solar flux, where a small portion is reflected back out to space because of the surface albedo, and the outgoing long wave flux from the surface. So once the incoming solar flux hits the ground, it's converted into thermal energy and radiated out. If you have a cloud present, this cloud also interacts with the radiation. So the cloud will absorb some amount of the outgoing long wave flux, convert it into thermal energy and re-emit it both up and down, but we're more concerned about the portion that's going back towards the surface. And so particularly at nighttime when the cloud isn't scattering any solar radiation, you have an additional component of long wave flux at the surface, and this warms the surface. This has been seen in the Gale crater where the Curiosity rover is. So Cooper et al. 2021, they noticed that during the aphelion cloudbout season, as the temperatures as observed by the REMS instrument on Curiosity are tending to increase, there was actually a local peak in these minimum air temperatures. And so they were looking into what is causing this local peak, and they were able to show that this small increase in daily minimum air temperatures is due to thermal re-emission from twilight and nighttime clouds. And so when you look at this figure here, during the ACB onset and peak, the amount of energy coming down from the atmosphere is more than when there is no clouds during the dust peak and the dust onset. And so how does that fit into this Phoenix project? Well, the Phoenix lander had a meteorological station, as I mentioned, and that contained 3 temperature sensors at 0.25 meters, 0.5 meters, and 1 meter from the lander deck, which was 1 meter off the surface. And importantly, this instrument took temperature measurements at a frequency of 0.5 hertz. And this meant that this instrument operated continuously throughout the entire mission. It took small breaks every sol just to send the data and stuff. But other than that, it operated the entire time. And so we have an entire record of temperatures throughout the mission, and we can exploit this temperature record to build a record of clouds. And so how do we do that? Well, we have to use a surface energy balance. And so this is the more complicated surface energy balance with all the components. So we have downwelling long wave flux from the atmosphere. So this is due to things such as CO2 in the atmosphere or dust. We have the solar flux minus the portion that's scattered back out to space. We have the sensible heat flux, which describes the exchange in energy between the surface and the atmosphere. And we have the outgoing long wave flux. And this component R is the term that we're most interested in this work, because it represents the emission, the thermal emission of energy due to clouds. So if clouds are present, R is some number greater than 0, and if no clouds are present, then R is 0. And so what we do is we model the ground temperature using several inputs that are reflective of the Phoenix landing site. So thermal inertia of the soil, there was ice, so how deep is the ice, and all this is put into a model. And once we found the ground temperature, we can find the air temperature by linking it to the sensible heat flux here. And so we model the air temperature with R set to 0, and then we compare this model temperature to the data collected from the MET temperature sensor. And then we add in R in 2-hour increments as needed to match the temperature. And this shows how much thermal emission there is from clouds and builds the record of clouds. So I'll show you what this looks like. So this is an example of a sol that has no cloud emission. So this is sol 9, and we actually only consider the time period between 10 so 10 p.m. to 10 a.m. Because during the day the atmosphere is very convective and this is not included in our model. And so we're just focusing on the time of day where radiation is dominant in driving the temperature. And so as you can see, the model temperature matches the Met air temperature very well. And so we don't need any thermal emission from clouds to match this temperature. So this plot is just completely empty. On the other hand, on Sol 137, the model temperature with R set to 0 is a few Kelvin colder than when we introduce R into the model. And so this represents the onset in the dissipation of clouds throughout the night. And so as you can see, you would need at least 20 watts per meter squared of thermal emission from clouds for the model temperature to explain the Met air temperature from 10 p.m. to 10 a.m. And so we do this analysis for every sol throughout the mission, and this is the record of clouds that we build here on the left. And so you can see that the cloud emission is variable throughout the mission. There are peaks and low points. We can see that the lowest amount of a cloud emission occurs just after summer solstice, and this is on this plot here on the right, is around the time when there are the warmest overnight temperatures. And when clouds are forming during this time, they're forming during the coldest part of the night, which makes sense. If it's not cold enough, then clouds can't condense and form. What's interesting about this analysis is that, as I mentioned, since the LiDAR didn't operate until Sol 38, we don't know if clouds formed in that time. However, this analysis shows that clouds were forming during this time, and so that's earlier than they are seen with the LiDAR or the SSI. Another interesting thing is that the peak in cloud emission towards the end of the mission from about Sol 90 onward is actually consistent with the arrival of the annular cloud at the Phoenix site. So the annular cloud is a reoccurring cloud phenomenon that happens every year in the northern polar region of Mars. And this cloud has been studied extensively from orbit. And the same year that the Phoenix mission was happening, it was noted that it arrived at the Phoenix landing site around Sol 90. And so that is reflected in this cloud record as well. We can also see how the clouds heat up the air temperature, as I mentioned, that with the additional amount of thermal radiation at the surface, this will induce a warming effect. And so as you can see that most temperatures are between 1 to 3 Kelvin, so a pretty moderate warming. Towards the end of the mission, you get up to 8.5 or so Kelvin. So those nights would be quite a bit cooler without clouds. And we can also look at how the clouds, on what scale the clouds form. So if you look at the energy balance and you integrate over a day to see the amount of energy per square meter received at the Phoenix site over an entire day, if you look at all the energy balance term, you can see that this is quite a seasonal effect. This makes sense because the energy balance is strongly driven by the solar flux and the outgoing long wave flux terms. And those are seasonally dependent terms. And so the whole energy balance has a seasonal dependence. But if you integrate the R term only, you can actually see that it is a lot more variable. So this indicates that clouds are driven by short scale effects, and that is shown by this high degree of sol to sol variability. The annular cloud, which I noted on the last slide, the years in which the temporal coverage of the cloud was really high, they noted as well that the annular cloud has a high degree of sol to sol variability. So that is shown in what we have here as well. And the last thing we're going to look at is how the water ice optical depth in cloud emission compares. So on the x-axis, we have water ice optical depth values retrieved from the LiDAR, and these are matched with the cloud emission values at the same sol and same time. The gray lines here are the cloud temperature. So what temperature would a cloud be that is emitting this amount of radiation? And these are about, between these gray lines are about the temperatures that we would expect for a cloud to be. And as you can see, hopefully it's a little bit scattered, but a cloud with a higher optical depth does emit more radiation towards the surface, which does make sense. However, this doesn't seem to be a hard rule. So these points here are emitting the same amount as this point, even though this one has a much higher optical depth. And this actually has been studied on Earth a little bit. So cirrus clouds, which form on Earth, which are also water ice clouds, they can be made of different ice crystal shapes, and two clouds that are the same optical depth but different ice crystal shapes will emit different amounts of radiation. And so this shows that we actually definitely need to constrain this cloud microphysical properties a lot more to understand specifically the cloud emission and how it interacts with water ice optical depth. And so that's all I have. So just to conclude what I talked about, we modeled clouds continuously at the Phoenix landing site by examining the radiative contribution to the surface energy balance. We could see that the clouds are variable throughout the mission, with the most cloud emission being seen in the last 50 sols. And we were able to see that optically thicker clouds tend to radiate more energy towards the surface. However, this definitely depends, not definitely, this may depend on ice crystal habit. And I recently had this work published, so my first published paper. So if you're interested, you can go check that out. And that is all I have. And if anyone has any questions, I'm happy to answer them.
Awesome. Thanks so much, Grace. Do we have any questions for Grace?
I have a question. That was a great talk. Thank you. And congratulations on the publication. That's so exciting. So I was just curious. So this lander was very close to the, I guess, North Pole. Would you expect the results to change if you were closer to the Martian equator?
Yeah, so there's actually, I mean, in terms of radiative forcing, clouds at the equator will also do that, which is what Cooper et al. Saw. But there is different clouds that form. So around the equator, during aphelion, when the planet's far away from the sun, you get the aphelion cloud belt, which doesn't quite reach up to the northern region where Phoenix was. So there are different types of clouds that form at different times of the year and in different locations on Mars.
That's so cool. Thank you.
Any other questions?
I could ask a question.
Go for it.
Thanks again for the great talk. Have you looked at connections with mesospheric cloud formation on Earth, particularly with the use of space launches increasing? We're actually hydrating the upper atmosphere. And so I'm just wondering if there are any clear connections that you can make from looking at the current structure of Mars for changes on Earth's upper atmosphere.
I have not made that connection at all, so I can't speak to that really.
No worries. Okay, thank you.
No problem.
Perfect. So if there are no further questions, thank you again, Grace.
You.
I'll pass this on to Regina to introduce Nick.
Well, after Haley's amazing introduction of the previous speaker, I don't know if I can match it, but it is really great pleasure to introduce Nick. I think everybody has met Nick. Yeah, I told you I was going to stumble upon this in the past workshops and whatnot, but let me guarantee you that he didn't always have the long hair. In fact, it's the product of the COVID. But in all this period that he's been working, he's actually made quite a bit of a contribution, especially while he was working at Honeywell in Ottawa as part of his internship opportunity. And you're going to be hearing about really, really exciting research that he's done in the last 2 years. And he's almost done, right, Nick? Yeah. Yes. So this is more or less the final step in getting his master's thesis done. It might be a slightly different presentation compared to other speakers today and in other previous seminars, but I'm really hoping that we can give you a little window to the engineering research world. So all yours, Nick.
Okay. Pull this up. Sorry, are you seeing the PowerPoint or are you seeing the background?
You're all good.
We're seeing we're not seeing the presentation mode. We're just seeing the slides.
You're seeing the slides? Okay.
There we go.
There we go. All right, wonderful. Okay, right. So good afternoon, everybody. My name is Nick, and my research these last 2 years for my master's thesis has been on thermal control design for a spaceborne on-chip optical phased array. This project, or the OPA project in general, has been a huge undertaking in collaboration run by Honeywell in collaboration with the National Research Council of Canada and the CSA, as well as several other university teams. I'm going to do my best to give you guys, for those who aren't familiar, an introduction to what we mean when we say photonics, and for this project, microphotonics. And I'll talk about the thermal phase shifters and how we approached essentially solving this problem for this novel technology. I'm going to dive into the research objectives that we had for this project, and I'm going to go over the hardware overview, the simulations that we've done, our method of data acquisition, and then the optimization and layout for our feedback control setup. And then, of course, at the end, the future work going forward that is currently in the works. So we've been getting a lot of mileage out of this quote, and it has been very good. So I'll reiterate once again for everyone that silicon photonics studies the generation, transmission, modulation, processing, and detection of light using silicon as the optical medium. And as such, photonics have become essentially an emergent technology to replace old RF infrastructure, where RF infrastructure is essentially limited by the frequency, bandwidths, and power through their systems. Photonics essentially blows past all those margins on every front, and it has been sort of decided to be the way forward with this respect. An optical phased array is essentially a transmitter module using this technology where multiple independent emitters are used to synthesize a coherent signal. So essentially, by controlling the phase of each independent emitter, the wave interference pattern that resolves at the end creates a distinct wavefront that is effectively steered. And so we can essentially point from transmitter to receiver from end to end. Using this technology means we can improve transceivers, receivers, remote sensing, space astronomy, LiDAR systems, the works. And what this means is that it's an enabling hardware for any future exoplanetary observations and platform designs going forward. So to give an example, if anyone is familiar with the TV series or read the books of The Expanse, whenever they mention sending a tight beam message, this is the technology they're speaking of. So how do we go about making this transmitter work, this optical phased array run? And this is to be done through the thermo-optic effect. So as a material heats up, the effective index of that material changes, and therefore the phase of light passing through it also changes. So we essentially tune the temperature of the waveguides of which the light is traveling through in order to have them be at different phases of when they reach the emitter at the end. The array of 100 thin wire elements is seen on the right, highlighted, as well as the circular emitter at the end. However, the thermal crosstalk created by these elements as they are toggled on and off at different powers affects essentially the adjacent waveguides along each side, which affects, of course, the amount of phase change that is being affected on each one. However, this effect can be minimized and made consistent through ideal thermal control at a constant set point. Given the thermal sensitivity of the system, what level of thermal control can be achieved through addition of an external thermal control system? This is the underlying fundamental question we seek to answer. And the size of this, like I said, is a microphotonics platform. So the phase shifters themselves are on the order of micrometers and nanometers, as seen in the bottom right with the electron microscope image, which was very cool to see. So what are our objectives overall? One was to design and integrate the testing hardware of the OPA chip, which was 18 by 18 millimeters, onto a PCB, and then set up and characterize the hardware for the experimentation. Second was to design and demonstrate the thermal behavior of the OPA. This was done through console multiphysics simulations to predict the thermal profile, as well as establishing the performance benchmarks experimentally for the best conditions that we could. Finally, the last objective was to design and optimize the thermal control software for the optical phased array. This was done through MATLAB Simulink with a feedback control loop for active control and data acquisition. This involved characterizing the thermoelectric cooler module, which is our actuator in this system, for modeling, as well as the proportional, integral, and derivative control or design optimization for settling time and overshoot, which were our main goal, which were our top priorities. So in terms of how this all came together on the hardware layer, the OPA assembly, as put together in a head and shoulders, knees and toes approach, had the chip bonded to its PCB integration phase, which was then modulated by the actuator, that being the thermoelectric cooler module, and then the heatsink pulling the heat off of that as well. So the optical control hardware adds the power to introduce the heat to the system. The thermal control hardware pulls the heat from the system, and then the heatsink just removes it entirely after it's been controlled. Our setup at York, after we had previously created a minor setup at Honeywell during our internship stage, is seen as such, with all the components in play here. The OPA and the PCB, that being the green board mounted up top, surrounded by everything. It was a bit of a jumble, but we did make everything fit, and everything was able to be powered on effectively. So what was the point of putting this all together? So with our simulations, we ran both 3D and 2D simulations to essentially resolve and simulate the heat transfer with the expected boundary conditions along the geometry. This demonstrates the relationship of the thermal crosstalk per active phase shifting element, because we knew that this effect could not be eliminated entirely. It could only be minimized and or made constant rather than being like aggressively non-linear. So by running the simulations, we now have a relationship that we can use as a bias to be accounted for in the optical control, which is decoupled from the thermal control on the other end. So our approach for controlling this in the hardware was to essentially use through data acquisition devices and MATLAB Simulink, just a straightforward feedback loop from which we are measuring the voltage signals coming off of our thermistor, our feedback temperature sensor, to be compared on our controller to our set point. So what does this mean in terms of optimizing our control design? So the optimization of a proportional, integral, and derivative controller depends on the settling time and overshoot of our actuator in response to the temperature generated by the OPA. PID control basically depends on implementing a gain constant against the error, or the difference between where you are and where you want to be, on the error signal, the integral of the error signal, and the derivative of the error signal, respectively. This involves compensating for the non-linear relationship of our actuator, our thermoelectric cooler module, as a function of the difference of the temperature internally between these two plates, as it is a Peltier module. As of writing and of putting this presentation together, optimized active feedback control from where we are at was able to maintain set point within 0.2 degrees and with settling times of around 20 seconds. Now, in order to validate our experimental results and not waste all our time just implementing PID values and then test them and seeing and going back and forth, we needed a platform to, like I said, both validate and to aggressively cycle through many different PID values in order to see which ones had the best results, both again in terms of overshoot and settling time. This was done through putting together a simulated version of the entire experimental setup, where we are where this involves combining the direct change of temperatures from the OPA as an actuator plant model and the thermoelectric cooler as its own actuator plant model. By summing these two together, we essentially have a comparison to what the thermistor would read in its active state, and that again is then compared to our set point from which the decontroller can then be designed and optimized. There were several approaches taken to the actuator plant model for the thermal, for the tech, because of its, again, being aggressively nonlinear with respect to where the fact that we were only running off of one feedback point. This was done through input-dependent gain, alternating actuator plant models, and a standard transfer function, but through the averages of all the experimental data we had taken up to this point. So we were running through a couple of those. So by essentially testing against the full range of voltage drops done on the OPA as it cycles up and down to change the phase all the way up and all the way down for each independent phase shifter, we're able to define the percentage overshoot and, again, the average settling times. And both through simulation and experimentation, these values can essentially be validated and effectively brought to their best point. And that is essentially what we've been doing for the last little while. And I am currently in the last phases of writing and putting this data together, which is great. So beyond the scope of this project and what we were hoping to achieve going forward are a couple of things. First was to revise the design for the PCB and general packaging of the chip, because it is such small scale. We wanted to have access for thermal control and the optical control for the other university teams, of course. The second iteration of the OPA chip has actually been designed and is currently in manufacturing. And as such, the PCB integration phase I've already designed the second version of that. They have that as well. Going forward, I also wanted to investigate PCB integrated thermistors and thermocouples as regular scale temperature sensors just are not as compatible for microsystems as they would be if they were further integrated. Again, this would reduce complexity of the hardware setup and increase the efficacy of the feedback response. We wanted to replace some limiting power hardware devices in our layout, again, to reduce the footprint and also to unblock some experimental limitations. But we had some power limits on our system, which hampered a bit of our experimental testing. And hopefully we wanted to ameliorate that going forward. And finally, the optional coupling between the optical and thermal control codes. These systems were entirely decoupled and separate as an initial requirement of the project. But in retrospect, integrating both of these controls while keeping them functionally independent would increase the performance, reduce overhead, and simplify the testing environment. And yeah, that's where we're at. So I hope most of that was clear. Thank you for your time. And are there any questions?
Persian, looks like Persian has a question. Go for it.
Yeah, Nick, great presentation.
Thank you.
I'm wondering, does RF currently do anything that photonics doesn't? Does it have any advantages over photonics?
The benefit of RF over photonics would be essentially the range from which it can operate over. So in standard RF architecture, you have a transceiver that will essentially broadcast out signal, and you can have essentially multiple receivers in different areas picking up on said signal, regardless of whether or not they were essentially like aiming at the transmitter. The downside downside of photonics going forward is that the optical signal is essentially like it's a beam. It's one independent beam that must be steered, pointed from the transmitter to the receiver. So if we're going for intersatellite communications, rather than just pointing your transmitter in the general direction and then broadcasting, the transmitter needs to be aligned specifically to that satellite 7,000 kilometers away, right to the receiver point, in order for the signal to be received and processed. That's a little bit of an oversimplification, but essentially this is why beam steering has been such an aggressively researched topic in this field of photonics. And then there have been several approaches with respect to mechanical systems, whether it be like micromirrors or other kinds of actuators. But the issue with all of those is that in the space environment, any additional points of actuation, whether it be mechanical or not, are just additional points of failure. And if something goes wrong, then something goes wrong and we can't fix it. So this is why the OPA, our project, the optical phased array, is a solid state device that has no mechanical joints or actuation to it, which is preferable. But yeah, I hope that answers your question.
That was really clear. Thank you.
So, do we have any other questions for Nick? Okay, if not, thanks so much, Nick, for the presentation. And we'll move on to Simone. And to introduce Simone, we have Professor Aaron Boley from UBC. Take it away, Aaron.
Hi, everyone. Thanks for being here. It is my absolute pleasure to introduce Simone Hagey. So Simone is a finishing master's student here at UBC, and she's going to be continuing on to do her PhD work. And I am very fortunate that she is continuing to work with me. She has a broad set of interests and amazing capabilities, in my opinion. So she has looked at analysis of data. She's able to run simulations. She understands observations, and she likes getting her hands on equipment and looking at instrumentation. She also takes time to get out of the office and enjoy the outdoors. Today, she's going to be telling us about a lot of the work that she's been pursuing, both as part of her master's and then also as part of the TEPS program and as an intern with Blue Sky Space and the Twinkle mission. And the work is focusing on the evolution of the orbital evolution of hot Jupiters. And with that, Simone, I am pleased to listen to your talk.
Thank you. That was a lovely introduction. Let me just share my screen here. Okay, I'm going to assume that everything's functioning. Just let me know otherwise. So yeah, thank you. I'm so excited that I get to speak in front of this audience for like a full 15 minutes instead of just the quick 3-minute thesis. I get to explain in more detail what I've been doing. So this is, as Erin said, this is, oh, how do I change slide? All right, there we go. So this is my master's project, which is also a paper that we'll be submitting later this month. And the purpose of this project is to search for long-term variation in the orbital periods of ultra-short period hot Jupiters. So what that means is that we're looking for transit timing variations, or TTVs, but that are spread over very long time scales and are indicating evidence of phenomena such as orbital decay or apsidal precession, which I will talk about further in a bit. But it all boils down to what is the future evolution of these systems where you have one massive gas giant planet orbiting super close to the host star? What does their future evolution look like? And the other aspect of this project that just kind of came about naturally is demonstrating the impact that citizen science data can have on understanding the long-term evolution of planetary systems. So switching slides, there we go. Okay, so what do we mean when we talk about transit timing? So the data that I have been working with is purely just the transit center time and associated uncertainty. So for this project, I haven't even been fitting light curves to get the transit time. I'm just taking transit center times at face value and working with those. So the transit center time for a planet on a fixed orbit with a constant orbital period, you can predict any given transit time based on this simple linear law. So you start with your reference transit time, whatever epoch you've decided is 0, and then you add the number of periods that have elapsed. So transit timing at its most simple form is just, if you have an unchanging orbit, it's just this simple linear law to predict any transit time you want. So what we call transit timing variations are any deviation from this linearity. And we study those through O minus C, or observed minus calculated plots. And a common application that you may have seen before is in studying multi-planet systems, because the other planets in a system, their gravitational tugs can pull the transiting planet back and forth and give you these periodic trends in the timing residuals. So this O minus C plots, these are important because what we're doing is we're removing that linear trend and just looking at what's left. What are the residuals? What cool things are going on that aren't just the usual march through time? So multi-planet systems are the common application you might have seen, but what we're interested for the purpose of this project is those systems with a single planet with an ultra short period, because that is where you get to look for tidal orbital decay. And this is what initially got me interested in this whole project. Orbital decay isn't the only thing that we're going to be looking at, as I'll explain, but this is what really sparked my interest in the first place. So tidal orbital decay is where you will have the orbit of this ultra close hot Jupiter shrinking over time until eventually it's fully engulfed by the host star. And I love this artist's interpretation of WASP 12b, where you've got this incredible mass loss as the planet is dying. So this equation here is how we can express this phenomenon. So what we have is a constant period derivative. Your period is getting smaller and smaller over time, and it's dependent on the factors you would expect: the mass ratio, the radius of the star, the semi-major axis of the orbit, but it also depends on this factor Q, which is called the stellar tidal quality factor. So there's been a lot of theoretical work in this field, but we cannot constrain the stellar tidal quality factor yet. But if we can measure the period decay rate, we can constrain that tidal quality factor and learn more about the detailed dynamics of the system. So measuring the orbital decay rate of these ultra close hot Jupiters is really important and a super cool thing that we're just starting to be able to do. So how do we actually detect that through the transit timing? So what I told you before is that for an unchanging orbit, we have this linear law. If we want to model the orbital decay scenario, what we're doing is we're adding a quadratic term to this linear trend with our constant period derivative being negative for decay because the period's getting smaller. Now, in this case, I've written it as dpde, so the period change for epoch, but it's just a simple conversion between that and per time. So very simple. So as you can see in this animation here, as the planet begins to decay, the period gets smaller, those transits are going to start happening earlier and earlier and earlier. And so, as you can see from the equation, if you have a negative period derivative, that gives you the transit times coming earlier, and that's something that we can actually detect. This animation is highly exaggerated, so just keep that in mind, but I wanted to show you what that actually looks like. So what happens is, to study the TTVs, we remove that linear model, and all we're left with is this quadratic term. So the decay of the orbital period induces a long-term quadratic TTV that we can see in those O-V plots that I mentioned before. And this is measurable on decade timescales. So what does that actually look like? Here's some data, or this plot is from one of the original papers that talked about the orbital decay of WASP-12b, which is currently the only planet that we know of that is indisputably decaying. Its period is changing at a rate of about minus 30 milliseconds per year, which doesn't sound like a lot, but it actually does make a pretty big difference over time. So what you can see on the top part there with the transits is you can actually see that quadratic trend. You can see that beautiful parabolic curve in the data. And so that is what we're looking for, essentially. We're looking for planets where if we look at all the transit times and we take away that linear model, we can see this quadratic trend. I also included the occultation equation because they use that in this paper, but you're just adding half a period, so it's not really that different. Now, something that you might notice, well, especially with these green lines on the plot, is that you could actually draw something that's periodic and still make it fit the data. Like, are we actually looking at a parabolic trend that will continue, downwards, or is it just that we happen to be looking at one of the peaks of something that is periodic and will come back up? Now, that's something that we do need to consider because there is a physical phenomenon that could give us something like that, and it is called Apsidal Precession. So Apsidal Precession is something that you naturally have when your orbit is still eccentric, even just a little bit. You will have the line connecting your periaps and apoaps of the orbit slowly rotate over time. So what that means is for the dynamics people, the argument of periaps, omega, will be increasing steadily. So I have the timing model included here. It's not super important to really stare at that. The point is that because the planet is moving faster at periaps and slower at apo, for half the precession period, you will have the transits coming earlier, and for half of the period, you'll have them coming late. And so just going back to that previous slide, that's why you see it could possibly give you, or it could give you this periodic up and down trend in your transit timing residuals. Because this happens on such a long time scale, when we're looking for evidence of tidal orbital decay, we need to consider this as a possibility. Now, it's not that this is some nuisance phenomenon that we need to consider. It is actually inherently interesting on its own, because if we can nail down a precession rate, we can learn more about the interior density distribution of the planet, which is in its own really cool. So either way, we're happy, but we do need to compare the two models. Okay, so I just threw a bunch of theory at you, but to summarize, the orbital decay of ultra short period exoplanets can easily be detected in their measured transit center times. It's a simple quadratic model, it's not difficult to fit, and clearly it will be visible in the transit timing data. But the caveat is that we need a long enough baseline of data. And that is the main issue facing this type of work right now, is that you need to have at least a decade, ideally more, as much as you can get, of a baseline of data in order to notice a change, because this happens slowly, relatively slowly. It's fast at astronomical time scales. So where do we get this data? That's something that I realized starting this project. We need lots and lots and lots of data. And that's where the Exoplanet Transit Database comes in. So this is a project that was established in 2008 by the Variable Star and Exoplanet section of the Czech Astronomical Society. And it allows any observer from around the world to upload transit observations. So it's a huge database, and it's still active and growing to this day. So there are over 400 planets. I just checked yesterday, over 12,200 observations submitted. There's a transit prediction tool that's super handy. So even if you're not planning to submit to the database, using their transit prediction tool can be very useful. And they have a light curve fitting tool integrated into their submission process. So what I noticed when looking at the database, which I had previously known, but I had never used their data for any research before, I looked at this plot of WASP 12b, which is that planet that we know is decaying. And I went, wow, look, you can really see the curvature in there. Like, it's very clear that even though this data has a lot of scatter, there's some spurious data points, you can still see this long-term trend. So what about the other systems? Can we use the data in this database to search for other systems that could be decaying? So we developed some methods for analyzing this data. We have a custom Metropolis Hastings MCMC routine that's built into an iterative sigma clipping algorithm. And that's what we use to scan through all of the targets and search for statistically significant quadratic curvature in the residuals. Now, we kind of developed this custom routine carefully because there is a lot of scatter in this data, and it's clear that probably some of the uncertainties are underestimated. So we took a careful approach to make sure that we weren't introducing any trends or clipping them away if they were there. In order to compare the models, the different timing models I introduced, we used something called the Bayesian information criterion, which is just like the chi-square that we all know and love, but it adds a penalty for the number of free parameters in your model so that you can fairly compare different models with different numbers of free parameters. So the lower the value, the better the fit. So if you look at our WASP-12 data, the BIC for the orbital decay is lowest, which means that that is the best fit, which agrees with the literature, so that's great. And not only that, but we did measure a decay rate of minus 34 milliseconds per year, which is compatible with all of the literature results. So that means that not only does this show that the citizen science observations can yield this evidence of this orbital decay that we do know exists for this planet, not only that, but our analysis routine is sound. So that's really exciting. So we applied this to other systems in the database. We had a certain criteria for how many numbers of data points the system had to have to be included in our analysis. So it's very possible that there are actual decaying systems that are on the database, but didn't have enough observations to meet our criteria. But out of the ones that we looked at 30 planets, and we have identified 8 systems on the database that show strong evidence of a statistically significant quadratic transit timing trend, which we interpret as orbital decay. So there's 7 new targets because WASP-12 is part of the 8. And by no means is this a declaration that these are decaying planets. This is a prioritization of targets for follow-up study. And in those follow-up studies, we plan to include data from professional observatories, so anything in the literature, test data, and then also try to solicit more observations. But this is really exciting because something that I noticed when doing background review for this project was that there's been a lot of back and forth in the literature about different targets. Is it decaying? Perhaps not. And it hasn't seemed like they're predictions for which planets will be decaying haven't turned out to be true a lot of the time. So I thought, why don't we use the data that we already have to prioritize follow-up studies rather than just kind of picking something and seeing if it works out. So hopefully this helps. And I'm really excited about it. This paper, this table is from the paper that we're going to be submitting soon. And the final aspect of what I've been doing is looking at what will future observatories be able to tell us, such as Twinkle, which is the telescope that I've been working with the Twinkle team for my internship, but also, you know, Ariel's coming up, and we have KOPS that's just that's still going. So there's lots of professional observatories, space-based observatories, and what could they tell us? And what I learned is that with the Twinkle telescope, even if we just have one transit per year for 3 years, if these planets are decaying at the rate we think they are, it will be enough to make that pretty much indisputable. And not only that, but cut the orbital decay rate uncertainties in about half. So this shows that we really truly are just at the cusp of being able to do this, and getting citizen science data to fill out these beautiful baselines, and then have professional observatories for some solid anchors in there. Within 5 to 10 years, that will be enough for us to confirm whether or not these planets are actually decaying. So hopefully I didn't go over time. I'd like to thank, of course, my collaborators, Aaron Boley, my supervisor, and Billy Edwards, whose affiliation I forgot to put on here, but he's at the CEA in Paris at the moment. And then, of course, this wouldn't be possible without all of the observers who are incredibly skillful and have great equipment. And I'm just continuously so impressed. And they're so dedicated. So you can see how widespread this project is. It's constantly growing, and my work wouldn't be possible without them. So I will be thanking them as well directly, but just so you know, I am very grateful, and you should check out the database. So thank you. I'm happy to answer any questions.
Thanks so much, Simone. That was great. Do you have any questions for Simone?
I have a question, if that's all right.
Yeah, go for it, Zhang.
So is orbital decay, is that like the fate for all ultra short period planets?
That isn't clear at the moment. There's I can't remember the name of the paper right now, but I've seen work where they predicted they say, you know, most of them will eventually decay like this. And then I've seen the number at 50%. Like, we're not really sure, but there is evidence in the demographics that suggests that it is widespread, like with the rapid rotation of a lot of hot Jupiter host stars. As angular momentum is transferred to the star, they spin up. So, you know, there's rapid rotation. There's a lack of hot Jupiters with periods of less than a day, which implies that maybe it's because they have died. So definitely not clear at the moment, but as soon as we can finally start getting some like more detections, then we'll be able to start making those kinds of conclusions.
So the determining factor is like the initial spin, like the initial angular momentum of the planet?
I wish I could answer that question. I don't know. I'm not sure. So for my PhD, I will be diving deeper into the more detailed dynamics. So I can't answer whether that's something I just don't know, or if it's something that in general the community doesn't know. But I think that because we don't have any more examples of a decaying system other than WASP-12, it's really hard to make those kinds of conclusions with data to back it up.
All right, I'm satisfied. Thank you.
When I know more, I will give another talk, and then you're welcome to ask me. We can talk about it.
Do you have any other questions for Simone? Oh, for Rushan? Yeah, go for it.
Hey, Simone. First of all, great presentation. I like that how you explained it really simply, super easy to follow. So my question is there a specific value or a threshold where you can say that the timing deviation becomes indisputable?
Oh, that's a good question. So I'll pop this up here again. So this Bayesian information criterion is kind of the best way that we have right now for saying whether or not the decay model fits better than just a constant period. And so this is the metric that the literature in this community uses. I'm not sure how widespread it is like outside of this community, but what's been happening is that if the difference between the Bayesian information criterion for two different models is greater than 10, then that's considered to be very, very strong evidence that that model fits better. So, I mean, if we're talking, so the Bayesian, the difference here is, you know, a couple hundred for WASP-12, that is indisputable. Now, you might have, if you had a keen eye, you might have noticed that my delta BIC here, my difference in Bayesian information criterion are very high. And so that indicates very strong evidence, but because of the high scatter in the data, we're being careful and not saying that this is a definitive detection. But in general, that's kind of the metric. I hope that answered the question. I think that's what you asked.
That was great. Thank you.
Okay, awesome. There's some cool statistics papers describing why that difference in 10 means something. I could not tell you right now, but it has to do with like the Bayesian odds ratios and stuff. So it's pretty cool.
Oh, cool. Thank you.
Cool. So I guess we'll end it there. Thank you again, Simone. And thanks to Grace and Nick as well for your presentations. And yeah, and we'll conclude this TEPS seminar, and we'll see you all next month for the next one. All right. Have a wonderful week, everyone. Take care.
Thank you. You too. Bye.
Thanks, everybody.
Thank you.